So in our third lecture for chapter 17, we're going to cover the last probability model that we're covering. In the first lecture, we talked about what Bernoulli trials are. Then we talked about the geometric model, which is a model that could help us find the likelihood that our first success occurs on a given trial or by a given trial or what have you. This last one is called the binomial model. And this is one that is going to stick around in various forms in the last unit. And uh, it's going to be one that we want to definitely be comfortable with because it's going to help us out a lot. What we're looking for, what we're talking about in using the binomial model is finding the probability of a certain number of successes in a fixed number of trials. Little different than the geometric model is we're not looking for just the first success, and we don't have unlimited trials. We have a set number of trials, and then we say, what's the likelihood that in that set number of trials we have this number of successes? And the same variations can be done up to this many, beyond this many, whatever it might be. And we'll talk about how to package these answers and how to use the calculator to help us out here. It looks a little, the parameters of the binomial model are the number of trials and the probability of success. Right? So we're going to look at binom. If we're going to name it, we would say we're modeling something with the binomial model with this many trials and this probability of success. Everything else that we can figure out from those. And what it looks like is the same variables are used, right? The same N, P, and Q. And just a reminder that in our formula sheet from the College Board, Q is 1 minus P, right? They don't use Q. They use 1 minus P, but it's the same. So all these formulas may look a little different on the formula sheet, but they should be there. And then what it looks like is that. Now that's something that this idea here, this C, is called a combination, and it's accounts for all the different ways we can get X number of successes in N trials. We don't do a lot with that in this text. They don't. Other textbooks will have a unit called counting principles where you'll do combinations and permutations and all that sort of thing. Here we're just kind of dressing it up. But if we're looking here, this kind of looks like the geometric model. And this number here, which is one that gets very big very quickly, is just accounts for all the ways that you can get those number of successes in the number of trials. Say we have 5 trials and we're looking for 3 successes, right? So we could have a success, a failure, a success, a failure, and a success. That's one way to get it. Or a success, a success, a success, and 2 failures, or vice versa, or reverse the order. There's lots of ways you can. There's this many ways to get it, where N is your total number of trials and X is the number of successes. We don't want to calculate that. We're going to dress that up, and we're going to dress all of this up, but then let the calculator do the heavy lifting. So don't worry about necessarily having all this down. You'll see when we go through the problem that you're doing what we've kind of learned to do in this course, which is I'm going to set it up as if I'm doing it by hand, but then I'm going to do it by use the calculator. So we'll go back to our trading cards in the cereal boxes. And so the type of question here is probability of finding 3 tiger cards in 10 boxes. If we're distinguishing the geometric from the binomial, if they give you a number of trials, then we're talking about a geometric. 9 times out of 10, we're talking about geometric, right? And so our 10 is the n, and our 3 is the x. And our probability of success is still 0.2, because that's success is finding what we're looking for, and we're looking for Tiger Woods cards. So how we would dress that up would look like this, right? We'd use the binomial model with an n of 10 and a probability of success of 0.2. And then we'd say, okay, the probability of that x is equal to 3, the number of successes is equal to 3, would look just like this. And really, there's a lot of things that you can kind of visually remember that is P then Q. So we have, this is our probability of success, this is our probability of failure. These numbers are going to be the same, right? And then this is going to be the what's left over, right? So these two numbers here, the exponents on the two probability of success and probability of failure, need to equal the total number of trials. Right? And that's all we, that's what we dress up. How we do it is if we plug it into the calculator, right? And the calculator needs 3 bits of information. So we go second vars. Now this is important. PDF. We never use PDF when you use normal, but when we're talking about binomial and when we're talking about geometric, I didn't really put any calculator input on the geometric. PDF is for a precise number. That's how I remember it. The P stands for exactly 1. So if you've got a probability statement here that has an equal, that should be binomial PDF. And what that will give you is 10 trials, the probability of success of 0.2, and X successes. We write that. We write this here. I know I kind of made it a little sloppy. I'll clean it up here. We write this, but we do, we do this, and they'll never know the difference, right? They'll never know the difference. So you have about a 20% chance that if you get 10 boxes, you'll get 3 Tiger Woods cards. It's not a guarantee, but that's the odds. These are models, and models are always wrong, but sometimes they're close, right? Another way is, what's the probability of finding 3 or fewer cards in 10 boxes? Now this is where we really want to be paying attention to our phrasing of the question, right? 3 or fewer Tiger Woods cards. So what we're looking for with that binomial model, again, we've got a finite number of trials, and we're looking for, in this case, 0, 1, 2, or 3, right? Because 3 or fewer. So 3 is something we need to count, right? Now we dress it up, and there's a lot here, right? We want to find the probability of that x is 0 plus the probability that x is 1, but so on and so forth. And we write that out, right? And having these actually, I think, kind of help, right? I think kind of help, because whatever this is here is your coefficient of your probability of success. Right? I have no idea why there are 2 decimal points there. There's nothing special about those. But this is just what we write. And if you want to do a couple, and then, I mean, this one is probably 6 of one, half a dozen of the other. You could do ... or you could do them all out. But you can use the ... and say 1, 2, ... and then do the last one. That's totally fine. That's communicating, yeah, I know what to do. I'm not just doing one thing, I'm doing multiple things, and I'm adding them together. How we use the calculator, since we're using this, since we've got less than or equal to, CDF. And since it's less than or equal to, that x value is what we put in. If it was just less than 3, we would put 2. Because whatever you put in here in this last spot will be the last one that gets added together. Will be the last number of successes that gets added into the group. So that's why you want to be really sure as to what you're doing and be able to write this accurately. whether it be less than or equal to. Right? And then as we look at so if we want to know how many we would expect to find, just like before, we have a mean and when we have a standard deviation. So we've got our binomial model with 10 trials, probability of success 2. How we come up with the mean and standard deviation, again, the mean behaves just kind of like we think it should behave, n times p. So if we have 10 trials and we expect 20% of them to be Tiger Woods cards, it's reasonable to think that, well, we would expect 2 Tiger Woods cards in that group of 10. Doesn't mean it's going to be, but that's what we would expect based on the probability of success. Standard deviation is the square root of n times p times q. And that's going to get a little messier, but that's, we would be able to do, we'd be able to calculate that. So we would expect 2 with the standard deviation of a little over 1 1/4. Now, why would we care about the mean and standard deviation? Well, what's nice about the binomial model is if the size, if we have a big enough sample, we can use the normal model to approximate the binomial distribution. So if we expect at least 10 successes and 10 failures, n times p is greater than or equal to 10, n times q is greater than or equal to 10, we can use that mean and standard deviation and whatever number we're looking for to find our that probability. It's not going to match up exactly by as it would doing it by the binomial model, but it won't be different enough to say like, oh, now I've got a different decision to make. You'd still make the same decision. Okay? So that's all we have for the binomial model. This is one that we're going to want to practice a lot in class, and we're going to get plenty of opportunity to do so. So, like I said, we will go over more in depth the calculator input, so you get well versed in that, and show you how to dress up the problems and how to make sure we're checking all the conditions, and then how to not only dress up but how to set up the problems so we can use the calculator to the best advantage. Right? So please let me know if you have any questions. Hope this helped.